Greedy algorithms. In Wall Street, the iconic movie of the 1980s, Michael Douglas gets up in front of the room full of stockholders and proclaims, "Greed is good, greed is right, greed works." In this chapter, we'll be taking a much more understated perspective as we investigated the pros and cons of short-sighted greed in the design of algorithms. Indeed, our aim is to approach a number of different computational problems with a recurring set of questions. Is greed good? Does greed work? It is hard, if not impossible, to define precisely what is meant by a greedy algorithm. An algorithm is greedy if it builds up a solution in small steps, choosing a decision at each step myopically to optimize some underlying criterion. One can often design many different greedy algorithms for the same problem, each one locally, incrementally optimizing some different measure on its way to a solution. When a greedy algorithm succeeds in solving a non-trivial problem optimally, it typically implies something interesting and useful about the structure of the problem itself. There is a local decision rule that one can use to construct optimal solutions. And as we'll see later in Chapter 11, the same is true of problems in which a greedy algorithm can produce a solution that is guaranteed to be close to optimal, even if it does not achieve the precise optimum. These are the kinds of issues we'll be dealing with in this chapter. It's easy to invent greedy algorithms for almost any problem. Finding cases in which they work well and proving that they work well is the interesting challenge. The first two sections of this chapter will develop two basic methods for proving that a greedy algorithm produces an optimal solution to a problem. One can view the first approach as establishing that the greedy algorithm stays ahead. By this we mean that if one measures the greedy algorithm's progress in a step-by-step fashion, one sees that it does better than any other algorithm at each step. It then follows that it produces an optimal solution. The second approach is known as an exchange argument, and it is more general. One considers any possible solution to the problem and gradually transforms it into the solution found by the greedy algorithm without hurting its quality. Again, it will follow that the greedy algorithm must have found a solution that is at least as good as any other solution. Following our introduction of these two styles of analysis, we focus on several of the most well-known applications of greedy algorithms. Shortest paths in a graph, the minima spanning tree problem, and the construction of Hoffman codes for performing data compression. They each provide nice examples of our analysis techniques. We also explore an interesting relationship between minima spanning trees and the long-studied problem of clustering. Finally, we consider a more complex application, the minimal cost arborescence problem, which further extends our notion of what a greedy algorithm is. Interval scheduling. The greedy algorithm stays ahead. Let's recall the interval scheduling problem, which was the first of the five representative scheduling problems. Which was the first of the five representative problems we have requests. We have a set of requests. The ith request corresponds to an interval of time starting at corresponds to an interval and finishing at f of I. Starting, note that we are slightly changing the notation, finishing from section 1.2 where we use the are slightly changing the notation rather than f of I. From section 1.2 where we'll make things easier to talk about in the proofs. We will say that a subset of the request is compatible if no two of them overlap in time, and our goal is to accept as large a compatible subset as possible. Compatible sets of maximal size will be called optimal. Designing a greedy algorithm. Using the interval scheduling problem, we can make our discussion of greedy algorithms much more concrete. The basic idea in a greedy algorithm for interval scheduling is to use a simple rule to select a first request I1. Once a request I1 is accepted, we rejected all requests that are not compatible with I1. We then selected the next request I2 to be accepted and again rejected all requests that are not compatible with I2. We continue in this fashion until we run out of requests. The challenge in designing a good greedy algorithm is in deciding which simple rule to use for the selection, and there are many natural rules for this problem that do not give good solutions. Let's try to think of some of the most natural rules and see how they work. The most obvious rule might be to always select the available request that starts earliest. That is the one with the minimal start time s of I. This way our resource starts being used as quickly as possible. This method does not yield any optimal solution. If the earliest request I is for a very long interval, then by accepting request I, we may have to reject a lot of requests for shorter time intervals. Since our goal is to satisfy as many requests as possible, we will end up with a suboptimal solution. In a really bad case, say when the finish time f of I is the maximum among all requests, the accepted request I keeps our resource occupied for the whole time. In this case, our greedy method would accept a single request, while the optimal solution could accept many. Such a situation is depicted in the subfigure 1a. This might suggest that we should start out by accepting the request that requires the smallest interval of time, namely the request for which fi si is as small as possible, fi minus si is as small as possible. As it turns out, this is a somewhat better rule than the previous one, but it still can produce a suboptimal schedule. For example, in the subfigure B, accepting the short interval in the middle would prevent us from accepting the other two, which form an optimal solution. In the previous greedy rule, our problem was that the second request competes with both the first and the third. That is, accepting this request made us reject two other requests. We could design a greedy algorithm that is based on this idea. For each request, we count the number of other requests that are not compatible and accept the request that has the fewest number of non-compatible requests. In other words, we selected the interval with the fewest conflicts. This greedy choice would lead to the optimal solution in the previous example. In fact, it is quite a bit harder to design a bad example for this rule, but it can be done, and we've drawn an example in the subfigure C. The unique optimal solution in this example is to accept the 4 requests in the top row. The greedy method suggests that here accepts the middle request in the second row and thereby ensures a solution of size no greater than 3. A greedy rule that does lead to the optimal solution is based on a fourth idea. We should accept the first request that finishes first, that is, the request I for which f of I is as small as possible. This is also quite a natural idea. We ensure that our resource becomes free as soon as possible, while still satisfying one request. In this way, we can maximize the time left to satisfy other requests. Let us state the algorithm a bit more formally. We will use R to denote the set of requests that we have neither accepted nor rejected yet, and use A to denote the set of accepted requests. For an example of how the algorithm runs, see figure 4.2. Okay, the algorithm is initially let R be the set of all requests and let A be empty. While R is not yet empty, choose a request I in R that has the smallest finishing time and add request I to A. Then delete all requests from R that are not compatible with request I. And while finally we return the set A as the set of accepted requests. Analyzing the algorithm. While this greedy method is quite natural, it is certainly not obvious that it returns an optimal set of intervals. Indeed, it would only be sensible to reserve judgment on its optimality. The ideas that led to the previous non-optimal versions of the greedy method also seemed promising at first. As a start, we can immediately declare that the intervals in a set A returned by the algorithm are all compatible. 4.1 A is a compatible set of requests. What we need to show is that this solution is optimal. So, for purposes of comparison, let O be an optimal set of intervals. Ideally, one might want to show that A is equals to O, but this is too much to ask. There might be many optimal solutions, and at best, A is equal to a single one of them. So instead, we will simply show that the size of A is equals to the size of O. That is, that A contains the same number of intervals as O and hence is also an optimal solution. The idea underlying the proof, as we suggested initially, will be to find a sense in which our greedy algorithm, stays ahead of which our greedy algorithm stays ahead of the partial solutions that the greedy algorithm constructs to initial segments of the solution O and show that the greedy algorithm is doing better in a step-by-step fashion. Some notation to help with this I1, I2, I3 until IK I1, I2, I3 until IK be in the set of requests. In the order they were added to the other node that the size of A is equals to K. In the order they were added to the set of a request in O be denoted by J1, J2, J3 until Jm. Our goal is to prove that K is equals to M. Assume that the requests in O are also ordered in the natural left to right order of the corresponding intervals, that is, in the order of the start and the finish points. Note that the requests in O are compatible, which implies that the start points have the same order as the finish points. Our intuition for the greedy method came from wanting our resource to become free again as soon as possible after satisfying the first request. And indeed, our greedy rule guarantees that f of I1 is less than or equals to f of J1. This is the sense in which we want to show that our greedy rule stays ahead, that each of its intervals finishes at least as soon as the corresponding interval in the set O. Thus, we now prove that for each R which is greater than or equals to 1, the rth accepted request in the algorithm's schedule finishes no later than the rth request in the optimal schedule. 4.2. For all indices R which is less than or equals to K, we have f of IR which is less than or equals to f of JR. Proof. We will prove this statement by induction. For R equals to 1, the statement is clearly true. The algorithm starts by selecting the request I1 with the minimal finish time. Now let R which is greater than 1, we will assume as our induction hypothesis that the statement is true for r minus 1, and we will try to prove it for r. As shown in figure 4.3, the induction hypothesis lets us assume that f of I r minus 1, which is less than or equals to f of j r minus 1. In order for the algorithm's rth interval not to finish earlier as well, it would need to fall behind, as shown. But there is a simple reason why this could not happen. Rather than choose a later finishing interval, the greedy algorithm always has the optimal at worst of choosing JR and thus fulfilling the induction step. We can make this argument precise as follows. We know, since O consists of compatible intervals, that f of j r minus 1 is less than or equals to s of j r. Combining this with the induction hypothesis, f of j I r minus 1, which is less than or equals to f of j r minus 1, we get f of I r minus 1, which is less than or equals to s of jr. Thus, the interval jr is in the set R of available intervals at the time when the greedy algorithm selects IR. The greedy algorithm selects the available interval with the smallest finish time. Since interval jr is one of these available intervals, we have f of IR, which is less than or equals to f of jr. This completes the induction step. Thus, we have formalized the sense in which the greedy algorithm is remaining ahead of O. For each R, the rth interval it selects finishes at least as soon as the rth interval in O. We now see why this implies the optimality of the greedy algorithm's set A. 4.3. The greedy algorithm returns an optimal set A. Proof. We will prove the statement by contradiction. If A is not optimal, then an optimal set O must have more requests. That is, we must have M which is greater than K. Note that the size M is the size of O and K is the size of A. Applying 4.2 with R equals to K, we get that f of IK, which is less than or equals to f of JK. Since M is greater than K, there is a request JK plus 1 in O. This request starts after request JK ends and hence after IK ends. So after deleting all requests that are not compatible with requests I1, I2, I3, and IK, the set of possible requests R still contains JK plus 1. But the greedy algorithm stops with request IK, and it is only supposed to stop when R is empty, a contradiction. Implementation and running time. We can make our algorithm run in time big O of n log n as follows. We begin by sorting the n requests in order of finishing time and labeling them in this order. That is, we will assume that f of I, which is less than or equals to f of j when I is less than j. This takes time big O of n log n. In an additional big O of n time, we constructed an array S of 1, 2, 3 until n with the property that Si contains the value S of I. We now select the request by processing the interval in order of increasing f of I. We always select the first interval. We then iterate through the intervals in order until reaching the first interval j, for which S of j, which is greater than or equals to f of 1. We then select this one as well. More generally, if the most recent interval we've selected ends at time f, we continue iterating through subsequent intervals until we reach the first j, for which S of j, which is greater than or equals to f. In this way, we implement the greedy algorithm analyzed above in one pass through the intervals, spanning constant time per interval. Thus, this part of the algorithm takes time big O of n. Extensions. The interval scheduling problem we considered here is a quite simple scheduling problem. There are many further complications that could arise in practical settings. The following point out issues that we will see later in the book in various forms. In defining the problem, we assume that all requests were known to the scheduling algorithm when it was choosing the compatible subset. It would also be natural, of course, to think about the version of the problem in which the scheduler needs to make decisions about accepting or rejecting certain requests before knowing about the full set of requests. Customers or requesters may well be impatient and they may give up and leave it if the scheduler waits too long to gather information about all other requests. An active area of research is concerned with such online algorithms, which must make decisions as time proceeds without knowledge of future input. Our goal was to maximize the number of satisfied requests, but we could picture a situation in which each request has a different value to us. For example, each request I could also have a value Vi, the amount gained by satisfying request I, and the goal would be to maximize our income. The sum of the values of all satisfied requests. This leads to the weighted interval scheduling problem, the second of the representative problems we described in Chapter 1. There are many other variants and combinations that can arise. We now discuss one of these further variants in more detail, since it forms another case in which a greedy algorithm can be used to produce an optimal solution. A related problem, scheduling all intervals. The problem in the interval scheduling problem, there is a single resource and many requests in the form of time intervals, so we must choose which request to accept it and which to reject it. A related problem arises if we have many identical resources available and we wish to schedule all the requests using as few resources as possible, because the goal here is to partition all intervals across multiple resources. We will refer to this as the interval partitioning problem. For example, suppose that each request corresponds to a lecture that needs to be scheduled in a classroom for a particular interval of time. We wish to satisfy all these requests using as few classrooms as possible. The classrooms at our disposal are thus the multiple resources, and the basic constraint is that any two lectures that overlapped in time must be scheduled in different classrooms. Equivalently, the interval request could be jobs that need to be processed for a specific period of time, and the resources are machines capable of handling these jobs. Much later in the book, in Chapter 10, we will see a different application of this problem in which the intervals are routing requests that need to be allocated bandwidth on a fiber optic cable. As an illustration of the problem, consider the sample instance in Figure 4.4a. The requests in this example can all be scheduled using three resources. This is indicated in Figure 4.4b, where the requests are rearranged into three rows, each containing a set of non-overlapping intervals. In general, one can imagine a solution using k resources as a rearrangement of the requests into k rows of non-overlapping intervals. The first row contains all the intervals assigned to the first resource. The second row contains all those assigned to the second resource, and so forth. Now, is there any hope of using just two resources in this sample instance? Clearly, the answer is no. We need at least 3 resources since, for example, intervals A, B, and C will all pass over a common point on the timeline, and hence they all need to be scheduled on different resources. In fact, one can make this last argument in general for any instance of interval partitioning. Suppose we define the depth of a set of intervals to be the maximum number that pass over any single point on the timeline. Then we claim 4.4. In any instance of the interval partitioning, the number of resources needed is at least the depth of the set of intervals. Proof: suppose a set of intervals has depth d, and let I1, I2, I3, and ID all pass over a common point on the timeline. Then each of these intervals must be scheduled on a different resource, so the whole instance needs at least d resources. We now consider 2 questions which turned out to be closely related. First, can we design an efficient algorithm that schedules all intervals using the minimal possible number of resources? Second, is there always a schedule using a number of resources that is equal to the depth? In effect, a positive answer to this second question would say that the only obstacles to partitioning intervals are purely local. A set of intervals all piled over the same point. It's not immediately clear that there couldn't exist other long-range obstacles that push the number of required resources even higher. We now design a simple greedy algorithm that schedules all intervals using a number of resources equal to the depth. This immediately implies the optimality of the algorithm. In view of 4.4, no solution could use a number of resources that is smaller than the depth. The analysis of our algorithm will therefore illustrate another general approach to proving optimality. One finds a simple structural bound asserting that every possible solution must have at least a certain value, and then one shows that an algorithm under consideration always achieves this bound. Designing the algorithm, let d be the depth of the set of intervals. We show how to assign a label to each interval, where the labels come from the set of numbers, the set 1, 2, 3 until d, and the assignment has the property that overlapping intervals are labeled with different numbers. This gives the desired solution, since we can interpret each number as the name of a resource, and the label of each interval as the name of the resource to which it is assigned. The algorithm we used for this is a simple one-pass greedy strategy that orders intervals by their starting times. We go through the intervals in this order and try to assign to each interval we encounter a label that hasn't already been assigned to any previous interval that overlaps it. Specifically, we have the following description. Sort the interval by their start times, breaking ties arbitrarily. Let I1, I2, I3 until In denote the intervals in this order. For j equals to 1, 2, 3 until n, for each interval I1 that precedes I2 in sorted order and overlaps it, exclude the label of I from consideration for ij, and for if there is any label from the set 1, 2, 3 until d that has not been excluded, then assign a non-excluded label to ij, else leave ij unlabeled, and if and for. Analyzing the algorithm, we claim the following. 4.5. If we use the greedy algorithm above, every interval will be assigned a label, and no two overlapping intervals will receive the same label. Proof. First, let's argue that no interval ends up unlabeled. Consider one of the intervals ij, and suppose there are t intervals earlier in the sorted order that overlap it. These t intervals, together with ij, form a set of t plus 1 intervals that all pass over a common point on the timeline, namely the start time of ij, and so t plus 1 should be less than equals to d, and thus t is less than equals to d minus 1. It follows that at least one of the d labels is not excluded by this set of t intervals, and so there is a label that can be assigned to ij. Next, we claim that no two overlapping intervals are assigned the same label. Indeed, consider any two intervals I and I prime that overlap, and suppose I precedes I prime in the sorted order. Then, when I prime is considered by the algorithm, I is in the set of intervals whose labels are excluded from consideration. Consequently, the algorithm will not assign to I prime the label that it used for I. The algorithm and its analysis are very simple. Essentially, if you have d labels at your disposal, then as you sweep through the intervals from left to right, assigning an available label to each interval you encounter, you can never reach a point where all the labels are currently in use. Since our algorithm is using d labels, we can use 4.4 to conclude that it is, in fact, always using the minimal possible number of labels. We sum this up as follows. 4.6. The greedy algorithm above schedules every interval on a resource using a number of resources equal to the depth of the set of intervals. This is the optimal number of resources needed.